lune as in lunar, and a lune in mathematics looks something like this.
And is that like the modern word for that? That's what you would...
That's what we would call it, I suppose, yeah.
It looks like a crescent to me.
Crescent, you could call it that. Well, this is a mathematical object that was of interest a number of millennia ago, and it's still of interest. We have a real sense of what Hippocrates of Chios, 5th century BC mathematician, he was interested in, can I say, even though this doesn't occur in his text at all, squaring the circle. So what does it mean to square the circle? What it means really is to find, at least the way I'm going to interpret it, is to find a polygon of the same area as the circle, and to find it in some constructive manner. What Hippocrates was interested in doing was finding the area of such figures in terms of the area of polygons.
He wanted to construct a polygon that had the same area as a lune.
As some lunes. He wasn't able to do it for all, or even in some sense very many, but he certainly was able to do it. And here's the starter lune. Starter lune begins with making an isosceles right-angled triangle, and here's the right angle, and thinking of that triangle as being inscribed, if you wish, in a semicircle. The next thing I would like to do is make another circle with this hypotenuse as chord. Well, I'd want to take either one of these snippets of circles, either this one or that one, they're both of equal area and equal shape. I'm going to try to view this line as the chord of a circle so that the figure I make will be similar to this one or that one. I'm going to try, because this is not all that easy, but I'll try to do it. Okay? So these three dashed things are similar. Let me draw it a second time and enlarge now. Now the question is, what can we say about the area of this guy in terms of the area of this guy, or equivalently in terms of the area of this guy, because the last two guys have the same area? Well, if you remember the Pythagorean theorem, this length is the square root of 2 times either of these lengths. So if the linear measure is the square root of 2 of the big segment is the square root of 2 times the linear measure of the small, either of the two small segments, what's the area of the big segment in terms of the area of either of the small segments? It's the square of the linear ratios. Okay, so this is twice the area of this, twice the area of that. Another way of saying it is this area is the sum of these two areas. So suppose I start with that triangle, and I'll draw it again, and I remove this blob, this area, and now I have to add something to keep the area of the triangle the same, and what I'm going to do is add the two small blobs. So what does that mean? That means that the area of the triangle is the area between these two semicircles. So what has Hippocrates done if he's done that? He has, in some funny way, squared this particular lune. This is a lune.
He hasn't squared it, though.
He hasn't squared it. He's
triangled
it. He's polygoned it, if you wish. Now, that's not where he ends his investigations, because
that's pretty clever, though.
It's already pretty clever. I think of this as the starter construction. This it's not clear in the manuscript, by the way, or the text that one has from his manuscript, whether he starts this way and this is his inspiration, but how can it not be? This is surely his starter lune construction. The minute you do that, you might imagine going into the business of squaring or triangulating or polygonating as many lunes as you possibly can. Let me start with the construction essentially with this straight line. So I'm going to make this the chord of a number of circles. Same line, but the chord of different circles. So it could be the chord of, well, could be the chord of I hope I'm going to draw it convincingly as a circle. Such a circle.
That's not the best circle I've ever seen.
Or it could be the chord, the same line could be the chord of this circle. Now, every time I think of this as the chord of a circle, I get a pie slice of that circle. I draw the line from the center to the two ends of the chord, and there's my pie. If I do it here, the pie slice would be pretty big. This is a rather generous portion of pie. How do we get our lunes? Well, we get our lunes by taking the same chord and making two circles with that as a chord of different radii, and thereby getting two different pie slices. Okay, like this.
So that's
going to be big, I guess. And like this, and that's going to be somewhat smaller.
And where's the lune here?
Here's my lune. Now, what turns out in each of Hippocrates' constructions is he's constructed his chord and his lunes in such a way that the area of this lune is exactly equal to the area of this little, what should we call it, polygon with a little
It's like a spearhead, isn't it?
Spearhead. And how does he do this? Well, by ingenuity. And he produces a number of examples. He does it by a certain process would be too long to give in this Numberphile, but he does it quite beautifully. Hippocrates manages to construct situations where the area of this pi wedge is equal to the area of this pi wedge. And so therefore they have a common area which is this, and that implies that this area is equal to this area. It is a consequence of a very careful choice of the radii of the two circles given the chord. There's a serious mathematical question which can be phrased in modern day mathematical vocabulary. It becomes a question in Galois theory. Has Hippocrates constructed all, or perhaps almost all, of the possible constructions given his methods?
Has he found all the lunes that can be spearheaded in this?
Spearheaded, wonderful word.
And what's the answer? Did he find them all?
Well, this is a conversation any modern mathematician can have with a 5th century BC mathematician. I don't know the answer. I worked on it a little.